In this class, we are going to study the post optimality analysis, or sometimes we call it as the sensitivity analysis also. If you see, your post optimality analysis is the study of changes in optimal solution due to changes in LPP parameters. The parameters mostly are AI, BI, AIJ, BI or CJ, which is called post optimality analysis or sensitivity analysis. So, basically we want to see the effect of the solution, optimal solution, whenever we are making changes in different parameters, mostly the parameter in the objective function, that is Cij, the matrix, that is Aij, that is coefficient matrix, and also the resource, that is Bj. So, whenever we change these parameters, actually what happens, or what is the change in the optimal solution, and you may ask why this is necessary. The objective of the sensitivity analysis is to reduce computational effort considerably, which arise when some error may appear to the data and requires the solving of the problem again and again from the beginning. This will help the calculations in the erroneous problem usable for the solution of the correct problem. So, basically if you see, sometimes what happens, you have a problem, but you have to change the parameters and you have to run the parameters, and whenever we are running the parameters, it is computationally it takes lot of time. So, if we can save the time by predicting something, that if this variable value is changing from a particular range, say from minus x to plus x, then the optimal solution will remain unchanged. In that case, you do not have to compute the problem again. So, you are saving basically the computational time, and for this reason sensitivity analysis is very much required for us. What we are going to study here is that following variations will be studied in post optimality analysis. Number 1 is variation in the cost vector C. Number 2 is the variation in the requirement vector B. Number 3, variation in the elements of matrix A. Then these are the 3 parameters which have been used. If you remember, our LPP problem is in the standard form, maximize z equals Cx subject to Ax equals B. So, the parameters involved are C, B and A. So, if I vary these parameters, what is the effect? Number 4 is addition or deletion of a new variable, means I can add a new variable or I can delete a variable, what will be the effect, and addition of a new constraint or deletion of a new constraint. So, we will study these things in this particular course. What is the effect of these variations? The effects, we say that the optimal solution remains unchanged, that is, your optimal solution will not change at all. The basic variables and their value will remain unchanged, and if we vary, second point is basic variables remain the same, but their value may be changed, that is, in the final basis whatever variables you got, after variation of the parameter, the basis variable will remain same, but their value may change. And number third point is the basic solution may change entirely, that is, you may get a new solution at together. So, these are the variations which you may get in your computation, that is, number 1 is your optimal solution may remain unchanged, and whereas the basic variables and their values also will remain unchanged. Your basic variable values may change, although the basis will remain as it is, and the entire solution may change. So, let us see the first one, that is variation in the cost vector C. Variation in cost vector C, and as you know, your cost vector is associated with the objective function. That is, if I write down in standard form the LPP, maximize Z equals Cx subject to Ax equals B and x greater than equals 0, the non-negativity condition. Now, suppose the parameter C is changed by delta C. Delta C equals, that is, the change in the vector C, we are telling that there will be a change of delta C, which you can write down delta C1, delta C2, like this way, delta Cn. So, the kth component you consider, just let us take only one component. So, if I take kth component of the modified cost vector, I can write down kth component of the modified cost vector Ck star, I am denoting it. Old value was Ck, new value is Ck star plus del Ck. So, your old value Ck has been changed to Ck star, where the new value Ck star is equals to Ck plus delta Ck. Now, what is the basic solution? Basic solution of your problem is xb equals b inverse b, which is fixed. So, if you see this solution b inverse b, which is independent of the cost vector C, So, from here this implies that the xb will remain unchanged. That is, current solution, whatever is there, that will remain the basic solution. Is it clear? I have changed the C vector, the kth component of C vector by Ck plus delta Ck, but we know the basic solution is xb equals b inverse b, which is independent of the vector C. Therefore, xb will remain unchanged. That is, the old solution will be the solution after the change from Ck to Ck plus delta Ck. So, if I make any variation in the cost vector or in the cost vector of the objective function C, then the basic solution will also remain unchanged. And also you know it, Zk minus Ck, this is equals Cb into Yk. If you remember, Zj minus Cj earlier we have computed as Cb into Yb. Yb is nothing but the variables x1, x2, x3, which I am denoting here as Yk. So, since this Zk minus Ck value is dependent on Cb, therefore, optimality criteria may change. Please note that optimality criteria may change, may not change. So, two conditions may arise. One is if your Ck does not belongs to Cb, this is one condition. Ck may not be belongs to Cb at all. In that case, optimal solution will remain unchanged. Optimal solution will remain unchanged. So, if Ck does not belongs to Cb, so it is not affecting the values. So, optimal solution will remain unchanged. And number 2 is, if Ck belongs to Cb, and if this is true, maximization of minus of Zj minus Cj divided by Yrj, which is greater than 0, less than equals delta Ck less than equals minimum of minus delta j minus Cj divided by y r j, where y r j may be less than 0. Then if your delta C k value lies in this particular range, maximum of this and minimum of this one, in that case the optimal cost Z star will be improved, and so optimal cost will be improved, and how much it will improve? It will be improved as delta C k into x k, because your cost has increased here by delta C k. That means, you will get more cost or more profit, and what is the extra amount? Extra amount is delta C k into x k. So, let us begin, start from the beginning. Whenever we have a change in the cost parameter, that is C, in that case there will be, since from here x b equals b inverse b, which is independent of C. So, there will be no change in the optimal solution, although z k minus C k, since this is equal C b into y k, this is equals to C b into y k. So, in that case optimal solution may change, whereas because here two cases may arise, C k does not belongs to C b, in that case optimal solution will remain unchanged, whereas if C k belongs to C b, in that case C k belongs to C b, and if this is true, delta C k lies between maximum of this value and minimum of this, then the optimal cost Z star will be improved by the quantity delta C k into x k. So, basically the feasible solution will not change at all whenever you are changing the value of the cost parameter C, but if you change the cost parameter C, then it may happen that your optimal cost may improve, and what is the improved quantity? Improved quantity will be delta C k into x k. Now, let us go to the next one, that is number 2 is variation in requirement vector. So, whenever you are talking about variation in requirement vector, so suppose your x b is the optimal basic feasible solution of the problem, maximize z equals C x subject to a x equals b, x greater than equals 0, and as usual A is the m cross n matrix. Now, we have told requirement vector means this B. So, suppose your B k is changed to B k plus delta k. Suppose your delta B k, the requirement vector B, the kth component of the requirement vector B changed from B k to B k plus del B k. So, what will be the new basic feasible solution? New basic feasible solution will be, say, x b star equals B inverse B star. This is equals to B inverse B star, where your B star is nothing but this one, B 1, B 2 like this way, and your B k has been changed to B k plus delta B k and B m. So, what is your x b star? Your x b star will be B inverse B. Your x b star is B inverse B star. If I write down this thing, then I can break it B inverse B plus B inverse. All this will be going out 0 0 like this way, delta B k, and this will be 0. So, this is nothing but this B inverse B is nothing but your x b, B inverse B, because your x b is equals to B inverse B originally, and then whenever I changed the kth component of B k from B k to B k plus delta B k, the new basic feasible solution has become B inverse into B star. So, this is I can write down x b plus beta k into del b k, where beta k is equals to kth column vector of B inverse, where beta k is equals to kth column vector of this B inverse into B k. So, please note this, beta k is the kth column vector of B inverse, and we can write it in the other way also. So, therefore, I can write down x b I star, this is equals to x b I. Now, I am generalizing it. So, beta I k into delta b k, where your beta I k will be the I comma kth element, I comma kth element of B inverse, where beta I k is the I comma kth element of beta inverse. Now, let us check the feasibility of this new solution. Feasibility means your x b I star should be greater than equals 0 for all I equals 1 to m. So, x b I star is greater than equals 0, which implies x b I from the value, by substituting the value of x b I star from the earlier one, this value. So, it becomes x b I plus beta I k into delta b k, which is greater than equals 0 for all I equals 1 to m, which implies again I can write down delta b k is greater than equals minus x b I by beta I k whenever beta I k is greater than 0, and your delta b k will be less than equals minus x beta I by beta I k whenever your beta I k is less than 0. So, from this expression I can write down these two, one for beta I k greater than 0 or beta I k less than 0. So, if I combine these two, the condition for feasibility will be maximum of minus x b I by beta I k, which should be greater than 0, is less than equals delta b k, which is less than equals minimum of minus x b I by beta I k, where beta I k is less than 0. Now, it is very easy to see one thing, that the requirement vector, the new solution will remain optimal, because the optimality condition is independent of beta. Your optimality condition is this one, z j minus c j, this is equal c b y j minus c j, which should be greater than equals 0. For optimality, this condition should be satisfied, and this is independent of B. Therefore, we can say that any variation in the requirement vector will not affect the optimality criteria, but it may affect the feasibility criteria. Please note this one. If your delta b k lies in this range, in that case the old solution will remain feasible and optimality criteria will not be changed. So, please note that for the requirement vector B, if the variation in B lies in this range, in that case your value of B, in that case the old optimal solution will remain unchanged, but otherwise if it does not lie, then the feasibility condition may change. So, please note that your optimality condition will never change, will remain unchanged, but feasibility condition may change if your value of the vector B does not lie in that range, that is maximum of that and minimum of that. So, if I know beforehand, you see the advantage of this testing the sensitivity, because if I have made a small change and if I see that it is lying in my range, I do not have to recompute the entire problem from the beginning. From this theory itself, we can directly tell that the solution is remains unchanged or solution will be the same. So, that is the basic criteria for this one. Now, let us come to the third point. Third point is change in the elements of coefficient matrix A. Other two, first one we have done change in the vector C, then we have done the change in the vector requirement vector B. Now, we want to say the effect of making changes or variation in the coefficient vector A. So, again we are assuming that x b is the optimal basic feasible solution of the problem, maximize z equals c x subject to a x equals b, x is greater than equals 0, where A is basically m cross n matrix. So, initially x b is the optimal solution of this problem. Now, suppose one element of A, say A r k, is changed to A r k plus delta A r k. A r k is changed to A r k plus delta A r k. Then the modified vector A k star can be written as this one, A 1 k, A 2 k, like this way, A r k plus delta A r k, like this way, A m k. This is the modified vector. Again, two cases may arise, that is your A k does not belongs to B or A k belongs to capital B. Your capital B is nothing but this matrix A B, your capital B is nothing but this one. So, case 1 where A k does not belongs to capital B. If A k does not belongs to capital B and your x b equals B inverse B, then optimal values of the variables will remain unchanged, because it is B inverse B and your A k does not belongs to this B. So, that means it is not affecting, therefore, the optimal values of the variables will remain unchanged. Now, let us see z k star. What is z k star? Z k star is C b into y k star, and this is equal C b into y b is nothing but B inverse into this one, B inverse into A k star. So, this equals I can write down C b B inverse into A k star is this one. So, from here I can, using earlier deduction, I can write it C b B inverse A k plus C b B inverse into, just like earlier one, 0 0 like this way, delta A r k like this way 0, and C b B inverse A k, this is nothing but the kth value of the z. So, this is z k plus C b into beta k into delta A r k, where again beta k is the kth column vector of B inverse. So, beta k is the kth column vector of B inverse after multiplication. So, this we are writing that your z k star is after changed, it is becoming z k plus C b into beta k into delta A r k. Now, for optimality, your z k minus C k should be greater than equals 0, we know it. For optimality, z k minus C k is greater than equals 0. So, this implies that z k plus C b into beta k delta A r k minus C k, this is greater than equals 0, or from here I can say delta A r k is greater than equals minus z k minus C k by C b into beta k, where C b into beta k is beta k is greater than 0, and also delta A r k will be less than equals minus z k minus C k by C b into beta k for C b into beta k less than 0, and delta A r k will remain unrestricted if this C b into beta k equals 0. So, combining we can write it again in this form, maximize of minus z k minus C k by C b into beta k, where the C b beta k is greater than 0 is less than equals delta A r k less than equals minimum of minus of z k minus C k by C b into beta k, which is less than 0, which I am writing like this way. So, therefore, what is the range of this one? The range is if delta r k lies in between maximum value of this to minimum value of this. In that case, what we are finding out that even if for variation in delta r k, there will be no change in the optimal solution. And please note that this we are doing it only whenever your A k does not belongs to B. So, if A k does not belongs to B, and if the variation in A k lies in this range, in that case optimal solution will remain unchanged. Otherwise, there may have some changes. So, whenever C b belongs to capital B, that we will see in the next class.